Hello and welcome to Lesson 6, 802.11 Wireless. Dialogue created and narrated by Don Keeber. In our last lesson, we looked at how open standards have arisen from the need to build vendor interoperability across multi-vendor platforms. We also briefly discussed the IEEE Computer Society when we touched on data link protocols like Ethernet and Token Ring. It happens that the IEEE Society, while having many facets of information, developed a set of standards dedicated to local and metropolitan area network architectures. This body of standards is subdivided into categories with a heading of IEEE 802.x, where x is a numeric value that describes the specific category. For example, IEEE 802.1 defines MAC bridging and switching technologies, and 802.2 define the LLC sublayer of the data link layer in the OSI model, and 802.3 defines the CSMA-CD functions of Ethernet. Following that same numeric convention, the IEEE 802.11 standard defines the functions of wireless LANs. We will find as we progress through this module that there are several extensions and amendments within the .11 standard. In this lesson, we'll dive into the IEEE standard as it relates specifically to the subcategory 802.11x. We'll break down the components that make up the .11 standard and explore the differences between the various subcategories. In order to fully appreciate the standard, we'll briefly discuss the 802.15 and 802.16 standards and explore the differentiators that make these standards unique. We'll also take a close look at the most commonly used wireless LAN technologies and their characteristics. The .11 standard specifically addresses wireless LAN medium access control, or MAC, and physical layer specifications. As a matter of information, the original standard was released in 1997 but not officially published until 1999. It was then reaffirmed in 2003 and has many amendments associated with it. The original technical reasoning and purpose for the standard, as indicated by the IEEE Society, was to provide wireless connectivity to automatic machinery and other equipment that required rapid deployment, which may be handheld or which may be mounted on moving vehicles within a local area. The 802.11 family includes over-the-air modulation techniques that use the same basic protocol. The most popular are two defined under the amendments .11b and .11g respectively. As previously indicated, the .11 standard was the first wireless network standard, but .11b was the first widely accepted, followed by .11g and more recently the 802.11n draft. It should be noted that the original or legacy form of the standard specified a 1 to 2 megabit bandwidth, which compared with today's networks is obsolete. The most recent amendments define a much richer 11 to 54 megabit capability. The security provided in the initial draft was purposely weak due to export requirements of some governments and was later enhanced via the .11i amendments after governmental and legislative changes. IEEE 802.11n is new and still under draft development. .11b and .11g use the 2.4 GHz Industrial, Scientific, and Medical, or ISM band. Because of this frequency band choice, .11b and .11g may suffer from interference from microwave ovens, cordless phones, and Bluetooth devices. It happens that both 802.11 and Bluetooth, which we'll touch on a bit later, control susceptibility to interference by using spread spectrum modulation. Bluetooth uses frequency hopping spread spectrum signaling, and .11b uses direct sequence spread spectrum signaling methods. .11a uses the orthogonal frequency division multiplexing method. Additionally, .11a uses the 5 GHz unlicensed National Information Infrastructure, or UNII band. In computer networking, a wireless access point, or WAP as it's sometimes referred, is a device that allows wireless-enabled equipment to connect to a wireless network using Wi-Fi, Bluetooth, and/or related standards. The WAP usually connects to a wired network and can relay data between wireless equipment such as computers, printers, and other peripherals to the LAN in question. Prior to wireless networking standards, setting up a computer network in a business, home, or school often required running many cables through walls and ceilings. With the advent of the wireless access point, network users are now able to add devices with few or no cables. Today's WAPs are built to support sending and receiving data using radio frequencies rather than cabling. Those standards and the frequencies they use are defined by the IEEE Computer Society. Despite the apparent advantages of a wireless infrastructure, the majority of WAPs in use today are in homes and small businesses. Due to the inherent security challenges, many larger companies shy away from using this technology. There is some confusion between wireless access points and ad hoc network connections. An ad hoc network uses connections between two or more devices without using an access point. The devices communicate directly. Ad hoc networks are essentially peer-to-peer connections and are not recommended for permanent installations. Wireless access points provide what is referred to as infrastructure mode connections. Many organizations will enforce company standards that dictate only infrastructure mode capabilities be allowed. A single WAP can typically communicate with 25 to 50 client devices, provided they are within the coverage area. Coverage areas can vary by product, antenna type, and building specifications. When a large deployment is planned, a detailed analysis called a site survey should be conducted. The output of this study will be a report that exposes possible coverage area problems such as nearby obstructions, electrical and radio interference, and floor plan constraints. Network designers can extend their respective coverage areas through the use of repeaters and reflectors, which can bounce or amplify radio signals that may ordinarily be outside of the operating range of the technology in question. WAPs can be configured as bridges and pointed using alignment procedures and may provide line-of-sight connections over several kilometers. A WAP can and should be configured with some form of security. Although the initial .11 standards only specified wired equivalent privacy or web security, later amendments such as 802.11i specify second and third generation security standards that are much stronger. Typical portable computers such as notebooks, laptops, and/or netbooks have wireless-capable interfaces built in. In many cases, these wireless cards come enabled by default. As a best practice, an owner of a portable computer should disable the wireless card and configure it for manual connections only. The justification for this practice will become evident as we proceed. This graphic demonstrates the configuration designs of ad hoc and infrastructure mode wireless architectures. Notice the apparent mesh connection paradigm with the ad hoc topology. The most obvious attribute of a peer-to-peer network is the sheer number of connections required to keep it up. Additionally, the security challenges with this topology make it next to impossible to use in any form of a production scenario. If you leave your wireless card enabled and with the default settings that allow ad hoc connections, you may unwittingly wind up joining such a network, especially in public surroundings. Infrastructure mode networks are hub-and-spoke designs that resemble a star topology. Wireless access points are gateways to some form of wired infrastructure and typically, but not always, require some form of passphrase or encryption key to gain access. The clients in an infrastructure mode network can be locked down and hidden from each other. When such a network is configured correctly, no one client can impact the security of another. With recent advances in technology, access points can be part of a unified management paradigm in which a wireless management controller can be associated with multiple WAPs to mitigate wireless roaming and association challenges. As I had stated earlier, it's considered a best practice and may be required when working on corporate networks to disable the computer-to-computer or ad hoc connection options. The screenshot on the left demonstrates the typical default wireless configurations of a Windows XP machine through Service Pack 1. Note the checkbox to automatically connect to non-preferred networks. You should leave that unchecked and select the middle radio button, Access Point Infrastructure Networks Only. Many wireless networks start small and grow over time. The simplicity of connectivity makes joining a wireless network desirable. However, it's crucial the security challenges with common connection topologies be a priority when building and/or joining these architectures. A few rules to consider when setting up a wireless network include the following. A strong authentication paradigm should be incorporated. The WAPs should comply with and be secured to IEEE 802.I standards. Network resources should be on separate VLANs with firewall protection in front of the wireless network. Vulnerability and penetration testing practices should be conducted periodically. If you are not directly involved with building a wireless network, then these rules should be the questions you ask before joining one. While there may appear to be a large number of standards, Most are actually amendments to the original and/or ratified .11 standard. Note the apparent performance enhancements as the amendments progress forward. There are also security enhancements that are introduced with .11i, not shown here. .11a is used in many private organizations due to the lack of commercial frequency interference problems and a number of non-overlapping channels. IEEE 802.15 and .16 respectively are wireless standards that address personal area networks and wireless metropolitan area or WiMAX networking standards. The .11n amendment is a new multi-streaming modulation technique that is still under draft development, but products based on its proprietary pre-draft versions are being sold. In this graphic, a screenshot from a TrendNet wireless N gigabit router is presented. Despite the fancy name, this is still just an access point. This device supports a proprietary spin on the .11n draft. Note that since the standard has not yet been fully adopted and published, this equipment could become prematurely obsolete if it winds up incompatible with the published standard when it becomes available. The manufacturers of this device have provided other compliant configurations that in fact do map to existing published standards, however, assuring investment protection, albeit a lesser standard. The Microsoft Windows Wireless Zero Configuration tool, available on most Windows XP and later desktops and notebooks, allows your computer to automatically configure itself for wireless networks to join. While this may be simple and convenient for home networking, it's a recipe for disaster in the vicinity of public hotspots. It's simple to overlook the security configurations on new access points when attempting to get your wireless design up and running fast. You should know that there are many people that would be more than happy to hop on your unsecured access point and make use of your resources, possibly the ones right on your computer. As we noticed a couple of slides back when looking at the configuration dialog for a TrendNet wireless access point, there were several choices when selecting which .11 standard to support. This feature is not unique to TrendNet. Most currently available wireless access points support multiple standards. The point of a standard is multi-vendor interoperability. Hence, an Apple computer should be able to connect to a Linksys gateway, and a Cisco or Apple access point should support the same connectivity for any Brand X computer. As we have seen, the first .11 standards were created in 1997 and formally published in 1999. The original published standard only supported a maximum network bandwidth of 2 megabits, which is too slow for most applications. For that reason, work began almost immediately on amendments to address these and other issues. In July 1999, the IEEE released the .11b specification. .11b supports bandwidth up to 11 megabits, comparable with traditional Ethernet. .11b uses the same unregulated radio spectrum as the original. While .11b was in development, IEEE created a second extension to the original called 802.11a. Because .11b gained in popularity much faster than did A, some folks believe that .11a was created after .11b, when in fact they were both created around the same time. Vendors often prefer building equipment based on the .11b frequencies to lower their production cost. Being unregulated, however, .11b gear can incur interference from microwave ovens, cordless phones, and other appliances using the same 2.4 GHz spectrum. This can be mitigated to a small degree by installing the gear at a reasonable distance from other appliances. Due to its higher cost, .11a is usually found on business networks, whereas .11b better serves the home market. .11a supports bandwidth up to 54 megabits and signals in a regulated frequency spectrum of 5 GHz. This higher frequency compared to .11b effectively shortens the range of a .11a network. The higher frequency also means .11a signals have more difficulty penetrating walls and other obstructions. Because .11a and .11b utilize different frequencies, the two technologies are incompatible with each other. Some vendors offer hybrid .11a-B network gear, but these products merely implement the two standards side by side. Each connected device must use one or the other. Although .11a gear is typically higher in cost, it's still a great fit for larger organizations. With .11x standards that support the 2.4 GHz spectrums, there is a significant challenge to overcome interference problems due to the large number of 2.4 GHz enabled equipment on the market today. To appreciate the capabilities and differentiators between the .11 extensions, it's crucial to understand the concept of channels. The .11 standards divide each of the bands into channels, analogously to how radio and TV broadcast bands are carved up, but with greater channel width and overlap. For example, the .11x 2.4 GHz band is divided into 13 channels, each 22 MHz wide, but spaced only 5 MHz apart, with channel 1 centered on 2.412 GHz and channel 13 on 2.472 GHz. Besides specifying the center frequency of each channel, the .11x standard also specifies a spectral mask defining a permitted distribution of power across each channel. The mask requires that signals be attenuated by at least 30 dB from the center, the sense in which channels are effectively 22 MHz wide. A consequence of this is that stations can only use every fourth or fifth channel without overlap, typically channels 1, 6, and 11 respectively in the U.S. Given the separation between channels 1, 6, and 11, the signal in any channel should be sufficiently attenuated to minimally interfere with the transmitter on any other channel. IEEE .11a operates in a much higher frequency spectrum of 5 GHz. Because of the higher spectrum, there are more available non-overlapping channels. It happens that .11a uses the Unlicensed National Information Infrastructure, or UNII frequency band. The UNII frequency band specifies 4 subcategories, low, mid, worldwide, and upper, within the spectrum. Each has specific sets of guidelines and rules associated with them. The non-overlapping channels of .11a are naturally separated by a 20 MHz width, effectively making the channels capable of having the full 22 GHz range when centered on the channel. The channel numbers are grouped by the UNII category. Channels 36, 40, 44, and 48 are grouped into the UNII low bands, for example, and channels 52, 56, 60, and 64 are grouped into the UNII mid-bands, and channel 149 is designated for the UNII high band. The IEEE 802.11g amendment was the third modulation standard for wireless LANs. It works in the 2.4 GHz band like .11b, and except for some additional overhead for backward compatibility, operates at 54 megabits like .11a. .11g hardware is fully backwards compatible with .11b. A very important consideration when working with .11g networks is that the presence of any legacy .11b participants will significantly reduce the overall bandwidth of the entire network. The reason this happens is the base modulation scheme on the access point reverts to the legacy scheme of .11b in the presence of any .11b clients. The modulation scheme used in .11g when operating in a pristine .11g environment is the same as .11a, orthogonal frequency division multiplexing. But as indicated, this scheme reverts to the legacy direct sequence spread spectrum of .11b when any .11b clients are present. .11g was rapidly adopted by consumers starting in January of 2003, well before ratification due to the desire for higher speeds and reductions in manufacturing cost. By the summer of 2003, most dual-band 802.11a/b products became dual-band tri-mode appliances supporting .11a, .11b, and .11g respectively. Despite its major acceptance, 802.11g suffers from the same interference as 802.11b in the already crowded 2.4 GHz spectrum. Additionally, the success of the standard has caused usage density problems related to crowding in urban areas. In this graphic, an access point that supports the .11g standard is visualized. Notice the option to enable Super G operation mode. Super G is a proprietary frame bursting, compression, and channel bonding technology used to improve on .11g performance. The throughput when using Super G is claimed to be up to 108 megabits, which is achieved through the bonding of two 54 megabit .11g channels. Super G was invented by Atheros Communication and has been made available through chipset enhancements by several vendors of wireless technology. Some vendors have licensed Super G and remarketed it as 108G and Extreme G. Critics of this technology argue that the non-standard channel bonding essentially hogs two or more channels in an already limited spectrum, causing issues with other wireless devices in the band, such as neighboring wireless networks, cordless telephones, baby monitors, and Bluetooth devices. It's important to note that Super G is not yet a published standard, and it does have competitors. Examples include 125 high-speed mode from Broadcom, MIMO-based extensions from Ergo Networks, and Nitro from Connexent. For this reason, caution should be considered when investing in one of these .11g enhancements. When a published standard does become available, some of these proprietary implementations may become incompatible. This table presents a matrix of 3 IEEE wireless standards. The chart provides an excellent reference to speed, range, and compatibility, as well as a few other considerations when planning a wireless network design. It's always a best practice to make these comparisons prior to making any substantial investment, and matrices such as these help to simplify the task by organizing the specifics of each standard side by side. You could get an already set up chart such as this, or you could create your own, building the concerns regarding the technology options as they relate to your specific requirements. This graphic demonstrates a theoretical topology design incorporating the 3 IEEE wireless standards, .11a, .11b, and .11g, respectively. The intent of this layout is to demonstrate the technologies as they relate to each other and their support for client access technologies. This diagram is purely theoretical, though. Most organizations typically would not implement all 3 technologies side by side. It is common, however, to find topologies incorporating .11b and .11g together as they interoperate fairly well. Many organizations will standardize on the .11a standard for all the reasons we have discussed. Note the switch with inline power in this diagram. Although beyond the scope of this course, it happens that the IEEE Society added an extension to the 802.3x body of standards, published as the IEEE Standard 802.3AF, which allows for powering devices to use a voltage of about 48 VDC over 2 of the 4 available pairs on Category 5E cable. This capability enables a wireless design engineer more flexibility when placing access points in places where typical power sources are unavailable, such as above ceiling tiles, outer walls, and on external towers where wireless bridges may be placed. The powering device may be a network switch or an inline power injector. In the latter case, the injector would be powered by an available power source and would essentially inject the necessary operating voltage for the wireless appliance onto the network cable along with the Ethernet signaling. To avoid data interference, the developers of this technology use low direct current voltages as opposed to alternating current, which would wreak havoc on the data. IEEE 802.11n builds on previous .11 standards by adding multiple input, multiple output, MIMO, and 40 MHz operation to the physical layer, as well as frame aggregation to the MAC layer. MIMO is a technology which uses multiple antennas to coherently resolve more information than possible using a single antenna. MIMO technology relies on multipath signals. Multipath signals are the reflected signals arriving at the receiver sometime after the line-of-sight signals have been received. In a non-MIMO-based .11a, B, or G network, multipath signals are perceived as interference, degrading the receiver's ability to recover the message information in the signal. MIMO uses the multipath signal's diversity to increase a receiver's ability to recover the message information from the signal. Another ability MIMO technology provides is spatial division multiplexing. SDM spatially multiplexes multiple independent data streams, transferred simultaneously within one spectral channel of bandwidth. MIMO SDM can significantly increase data throughput as the number of resolved spatial data streams is increased. Each spatial stream requires a discrete antenna at both the transmitter and the receiver. MIMO technology requires a separate radio frequency chain and analog to digital converter for each MIMO antenna, which translates to higher implementation costs compared to non-MIMO systems. 40 MHz channels are another feature incorporated into .11n, which doubles the channel width. This allows for a doubling of the data rate over a single 20 MHz channel. It can be enabled in the 5 GHz mode or within the 2.4 GHz if there is knowledge that it will not interfere with any other .11 or non-.11 such as Bluetooth systems using the same frequencies. Two important benefits it provides to .11n are antenna diversity and spatial multiplexing. It's expected that the formally ratified version of .11n will be released toward the end of 2009. There are several consumer and enterprise class products available as pre-standard devices. These products comply with Draft 2.0 of the emerging standard, and vendors are banking on that specification not changing significantly. It can be assumed that vendors will resist modifications that make shipping products difficult to upgrade. Right or wrong, this is stabilizing .11n and diminishing the risk of deploying it. One of the primary reasons network owners adopt .11n is speed. At the data rates mentioned above, .11n is about 4 times the speed of a .11g network. Another is better in larger coverage areas. .11n access points offer greater range and promise to reduce the number and size of dead zones. This translates to better aggregate coverage and simpler management. .11n highlights 2 advantages inherent to all wireless LANs: flexibility and cost. The following is some pitfalls that may arise in early deployments of .11n networks. The capacity of existing wired LANs must be sufficient to support the aggregate .11n traffic volumes. Replacement of existing APs and other RF management considerations will change, requiring adjustments for increased power output. Some .11n APs require greater power than what today's standard Power over Ethernet equipment supplies. New security considerations come into play associated with the 802.11n extended coverage range and new frame formats. A personal area network, or PAN, is a computer network used for communications among computers close to one's person. The reach of a PAN is typically a few meters. PANs can be used for communication among the personal devices themselves or for connecting to a higher-level network and possibly the Internet. Personal area networks may be wired with computer buses such as USB and FireWire. A wireless PAN can also be made possible with network technologies such as infrared, Bluetooth, ultra-wideband, Z-Wave, and Zigbee. It happens that the IEEE 802.15 is the 15th working group of the IEEE 802 and specializes in wireless PAN or wireless personal area network standards. There are 7 task groups associated with this subcategory of the 802.x body of standards. The task groups are numbered from 1 through 7 and individually focus on specific areas. Task Group 1 was focused on Bluetooth as it relates to the initial version 1.1 specifications and the later updated version 1.2, which was published as IEEE 802.15 1-2005. It was decided after the initial publication, however, to discontinue the relationship with the Bluetooth Special Interest Group, or SIG, effectively meaning that the later versions of Bluetooth will not become future IEEE standards. Versions 1.0 and 1.0b have many problems, and manufacturers had difficulty making their products interoperable. Work continues without the IEEE involvement and is currently at version 3.0. Future versions are still planned. The other task groups associated with the IEEE 802.15 are Task Group 2, which is chartered for coexistent issues, Task Group 3 for high data rate wireless personal area network developments, Task Group 4 with low rate wireless PAN development and includes Zigbee. Task Group 5 is chartered with mesh networking designs, and 6 is chartered for developing technologies based on body area networking, or BAN. Task Group 7 is chartered for Visual Light Communications, or VLC, although no work has been officially started with this group as of this writing. The Bluetooth specification was developed in 1994 by Ericsson Mobile Platforms in Sweden. The signaling technology is based on frequency hopping spread spectrum. The specifications were formalized by the Bluetooth Special Interest Group, or the SIG. The SIG was formally announced in May of 1998 and today has a membership of over 11,000 companies worldwide. It was established by Ericsson, Intel, Toshiba, and Nokia, and later joined by many other companies. Bluetooth and Wi-Fi has many applications in today's offices, homes, and on the move, setting up networks, printing and/or transferring presentations and files from PDAs to computers. Both are versions of unlicensed frequency band wireless technology. The primary differences between Wi-Fi and Bluetooth are noted in the purpose and typical applications of these two standards. Wi-Fi, for example, is intended for residential equipment and its applications. The category of applications is outlined as wireless LANs. Wi-Fi is intended as a replacement for cabling for general local area network access in work areas. Bluetooth, on the other hand, is intended for non-resident equipment and its applications. The category of applications is outlined as wireless PAN or wireless personal area networks. Bluetooth is a replacement for cabling in a variety of personally carried applications in any ambience, such as telephones, PDAs, gaming equipment, and I/O devices like keyboards and mice. The IEEE 802/2001 standard describes a metropolitan area network, or MAN, as a network that is optimized for larger geographical areas than a LAN, ranging from several blocks of buildings to entire cities. Technologies centered on wireless MANs are often referred to as WiMAX, meaning Worldwide Interoperability for Microwave Access. The name WiMAX was created by the WiMAX Forum, which was formed in June of 2001 to promote conformity and interoperability of the standard. The original technology specified using a variety of transmission modes, from point-to-multipoint links to portable and fully mobile Internet access. The original specification provided for broadband speeds of up to 3 megabits. Businesses initially adopted this technology as a redundant last-mile wireless connection alternate to cable modems and/or DSL. The technology is based on the specifications defined under the IEEE 802.16 standards and is also referred to as broadband wireless access. IEEE 802.16 is a series of wireless broadband standards currently published under IEEE Standard 802.16-2009. The working group was established in 1999 to develop standards for the global deployment of broadband wireless metropolitan area networks. Although the body of standards is officially called Wireless MAN, it has been commercialized under the name WiMAX. The most popular implementation of the standard is the Mobile Wireless MAN, originally defined by the .16e 2005 amendment that is now in the process of being deployed around the world in more than 140 countries by more than 475 operators. It's important to know that because the IEEE only sets specifications but does not test equipment for compliance with them, the WiMAX Forum runs a certification program wherein members pay for certification. WiMAX certification by this group is intended to guarantee compliance with the standard and interoperability with equipment from other manufacturers. The mission of the forum is to promote and certify compatibility and interoperability of broadband wireless products. The .16 standard essentially standardizes two aspects of the air interface: the physical layer, .16e, and the media access control layer, or .16 MAC. .16e uses scalable orthogonal frequency division multiple access to carry data supporting channel bandwidths of between 1.25 MHz and 20 MHz with up to 2,048 subcarriers. It supports adaptive modulation and coding so that in conditions of good signal, a highly efficient 64 QAM coding scheme is used, whereas a more robust binary phase shift keying is used when poor signaling conditions exist. Other physical features include support for MIMO antennas in order to provide better support for non-line-of-sight characteristics. The .16 MAC specification describes a number of convergent sublayers which describe how wireline technologies such as Ethernet, ATM, and IP are encapsulated on the air interface and how data is classified, etc. Additionally, the .16 MAC describes how secure communications are delivered by using secure key exchanges during authentication and encryption using AES and DES ciphers during data transfer. A key feature of .16 is that it is connection-oriented technology. The subscriber station cannot transmit data until it has been allocated a channel by the base station. This allows .16e to provide strong support for quality of service. An example of a typical connection scenario is visualized in this graphic. A subscriber station sends wireless traffic at speeds ranging from 2 to 155 megabits from a fixed antenna on a building. The base station receives transmissions from multiple sites and sends traffic over wireless or wired links to a switching center using the protocols defined under the .16e specifications. The switching center sends traffic to an internet service provider or public switch telephone network. This graphic further illustrates this feature and demonstrates a common .16 infrastructure. Note, the subscriber station can be a home, an office building, or a public hotspot. The base station is typically a point of presence and/or WiMAX tower, typically with a line-of-sight connection. This graphic also presents the concept of a point-to-point backhaul infrastructure used to connect multiple base stations. Note, the backhaul infrastructure will typically connect to a telco or service provider core with access to the internet backbone. This infrastructure design speaks to the physical layer of the specification. The MAC layer would be some form of transport like ATM, FDDI, or SMDS, and more recently Ethernet. In this illustration, a coverage area comparison map is presented to demonstrate the relative expected coverage areas offered in the IEEE 802.x specifications. As you can see, the personal area network has the least coverage area and consists primarily of close proximity devices like keyboards, mice, cell phones, etc. Moving out, we see that LAN infrastructures have greater coverage area and offer greater flexibility with recognized standards. Wireless LANs fall into this boundary. Next, we have the metropolitan area networks, including WiMAX. The range in these infrastructures can be from several buildings to entire cities. And on the outer perimeter of the spectrum is wide area networks, or WAN infrastructures. Note the proposed IEEE 802.20 specifications have already been chartered, but little or no notable work has been done in this area. So, to summarize our lesson, we dug a bit deeper into the IEEE 802 standards. We also broke down the many variants to the .11 standards and explored specific components, specifications, and topologies. We saw how the .11 amendments have progressed to bring enhancements to the original specification and how each of the amendments is different. We learned about different signaling technologies and how certain .11 amendments define changes to the wireless paradigms. We also saw how .11b and .11g are close cousins, and yet .11a, that was developed around the same time as .11b, offered a completely different and ultimately better way to accomplish the same goals. We briefly explored personal area networks, or PAN standards, with the .15 specifications, and we explored the IEEE 802.16 wireless metropolitan area network and WiMAX standards and how they are being deployed. We also saw how an organization sometimes has to weigh risk to benefit when choosing emergent technologies that have not yet been standardized. A key point to take with you is that .11 standards are evolving and will continue to define new and challenging ways to communicate network data without the need for cables or wired infrastructures. We hope you have enjoyed this video.